Remember that we investigated whether the happiness of children in rural areas is different than in the country as a whole, and we saw how to answer that question with a hypothesis test. However, what if we want to formulate a different research question? For example, is the happiness of children in rural areas different than in urban areas? Or, within urban areas, is the level of happiness the same in the three largest cities of the country, Amsterdam, Rotterdam, and The Hague? What if we want to study a different type of outcome? Say, the prevalence of overweight instead of the level of happiness. What kind of hypothesis test to use? In this lecture, you will learn how to choose among the most commonly used methods for testing for differences between groups in a numerical, categorical, or time-to-event outcome. Just as a preview, this will be the decision tree which we will cover in this lesson. We will go through it step by step, and in the end you will easily find your way through it. I must warn you that this video might be a bit long, but that we need the time to explore the decision tree. When deciding which method to use, the first important issue is the type of outcome you have: numerical, categorical, or time-to-event. If we have a numerical outcome, such as the happiness score we discussed before, we should zoom in on the numerical data part of the decision tree. The next decision to be made is how many groups do we want to compare. The case of comparing a single group to an overall fixed quantity we covered in the last lesson, when we investigated if the happiness of children in rural areas differed from those in the country as a whole. Let us now focus on comparing a numerical outcome between two groups. In our example, we would like to test if there is a difference in happiness between children from urban and rural areas. To choose the right method, we need to consider one extra issue. We need to determine if the groups are paired or unpaired. In our example, the groups are unpaired. Every child belongs to only one of the groups. Children are unrelated, independent of each other. However, imagine that we would like to know if younger siblings are happier than their older siblings. We say that the groups are paired, since each sibling is related to exactly one other sibling. When comparing older and younger siblings, we need to take into account the relationship that they have with each other. The most common test for comparing a numerical outcome in two groups is the unpaired or two-sample t-test if groups are independent, or the paired t-test if groups are related. The null hypothesis in the two-sample t-test is that the means in the two groups are equal. The test can be used when we have a sample that is large enough. A rule of thumb is over 25 per group. If the underlying distribution is approximately normal, the t-test can also be used with small samples. Since we assume a normal distribution over the groups, we call this test a parametric test. Sometimes our data is very skewed, even after trying some data transformation. We can then opt for a non-parametric test, since such tests do not rely on the normality of the data. An often used non-parametric alternative to the unpaired t-test is the Mann-Whitney U-test, and a non-parametric alternative of the paired t-test is the Wilcoxon signed rank test. What if we are interested in comparing three groups? For example, to test whether differences in happiness level exist between the three largest cities of the country. To compare a numerical outcome in more than two groups, we need different methods. The most commonly used is called analysis of variance, or briefly ANOVA. This method tests the null hypothesis that all groups have the same mean. Let's move on to the categorical part of the decision tree. Now we want to check if a categorical outcome differs between two groups. Recall that categorical data are summarized in terms of frequencies and proportions, so we will use those to formulate our null hypothesis. For example, we can investigate the null hypothesis that the proportion of children with overweight is the same in rural and urban areas. As in the case of numerical data, we need to first determine if the groups are paired or unpaired. When comparing rural and urban children, the groups are again unpaired. There is no relation between children from urban and rural areas. We can now compare the expected proportions under the null hypothesis to the observed proportions. Let's see how this works. Imagine that we have a sample of 100 children, 50 living in the countryside and 50 living in cities. This cross table summarizes the sample proportions we have obtained. In our sample, 6 out of 50 children from rural areas are overweight, versus 10 out of 50 children from urban areas. What would we expect if the null hypothesis is true? The same proportion of overweight in both groups. In total, we observed 16 overweight children out of 100, so if the null hypothesis holds, I would expect 8 of them to live in the countryside and 8 in the city. To test if the difference between observed and expected proportions is large enough to conclude that the proportions in both groups differ at the population level, we often use the chi-square test. This test compares the observed table with the expected table. Like with the t-test, we need to be careful with small samples. In a smaller sample, some cells in the crosstab only have one observation. For such tables, we should not use the chi-square test, but rather Fisher's exact test. Just like we've seen with numerical outcomes, when the groups are paired, we need a different test. For comparing paired categorical data, we use McNemar's test. An example of paired categorical data would be when we want to compare overweight of children before and after an intervention to increase their physical activity. Finally, for time to event outcomes, we often use the log-rank test. Remember that we usually describe this type of data by plotting the Kaplan-Meier curve. The null hypothesis of the log-rank test is that the survival curves of the two groups are the same, and the alternative that they are different. The log-rank test is actually a chi-square test, adapted for time-to-event data. At each time point, it calculates the expected number of events if there was no difference between the groups. Then it compares the observed with the expected number of events at each time point. In summary, when deciding which statistical test to use, we take 4 issues into account, which are summarized in the decision tree. First, whether the outcome is numerical, categorical, or time to event. Second, the number of groups to be compared. Third, if the groups are paired or unpaired. And finally, whether the groups are large enough. You will practice in the next reading activity and practice quiz which test to use when and how these tests actually work.